right, we are now looking at Chapter 7, Introduction to Terminating Decimals. And we're going to start with what is a finite decimal. And a finite decimal is a decimal which comes to an end, which terminates. So therefore, it's a rational number. Again, we're talking about fractions. So this is rational. So anytime you can turn a fraction into a decimal, it's rational. Anytime you can turn a decimal into a fraction, it's also rational. So let's first go back over and take a look at some place value, just to refresh your memory as an adult. So let's say I just take the digits 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I put a decimal between the 4 and the 5. So just to refresh your memory, as we go through this, we've already talked about whole numbers. So the 4 would be in the ones column. The 3 would be in the tens column. Then we would have the 100 column. And then we would have the 1 in the thousands column. So just like we did with the blocks and just like we did with the flats, the longs, the units, 1, since this is base 10, would be 10 to the 0 power. The 3 would be in the 10 to the first power. The 2 would be in the column of 10 to the second. And the thousands would be 10 to the third, which is 1,000. And I am going to say that this is in base 10. Therefore, all of the exponential expressions will have a base of 10. Now, as we go to the right of the decimal, we're getting smaller. And if we just go and recognize the pattern, our exponents goes from 3 to 2 to 1 to 0. So the next place would be to the -1 power. Then the 6 would be in the -2 power column. If I keep following this pattern, there we go. And of course, as we name them, now we don't have, if I look at 10 to the -1, that's the same as 1 over 10, which is in the tenths with an S column. 10 to the -2 would be 1 over 10 squared, which is 1 over 100. So that is the hundredths column. 10 to the -3 would be in the thousandths column. THS. 10 to the -4 would be 1 over 10,000. So this would be in the 10 thousandths column. And the next would be in the 100 thousandths column. So it's a mirror image of the whole number side, other than the fact that we don't have a 1 over 1, which is just 1. And so this is how we compare them up. So let's take a look first and expand the following, exactly like we did back when we were doing the bases in a previous chapter. So let's take a look at expanding, or an expanded form. Let's say I give you 1 times 10 to the third plus 2 times 10 squared. If I just look at this, this would be 3 times 10 to the first. This would be 4 times 10 to the 0. And if I keep going, I'm going to have 5 times 10 to the -1. 6 times 10 to the -2. 7 times 10 to the -3. 8 times 10 to the -4. And 9 times 10 to the -5. Remembering, of course, since we're in whatever base we're talking about, decimals will always be base 10. You make sure you have a term using every one of the powers of 10. And if we're missing a term, we insert a 0. So let's say, for example, I would like you to expand 235 and 87 hundredths. So let's start with the 2. This would be 2 in the third column. Well, remember it goes 10 to the 0, 10 to the 1, 10 to the 2. And now, once we've started that one and we figured out where that first decimal, that first place is, we can go in descending order for the powers. So this is 3 times 10 to the 1 plus 5 times 10 to the 0 plus 8 times 10 to the negative 1 plus 7 times 10 to the negative 2. And now at this point, we might be able to kind of work. Sometimes you can see it this way. You might see these last two, however, written as 8 times 1 over 10 and 7 times 1 over 100. So in true expanded form, I would keep it with the powers, but recognize it's improper to keep a negative exponent, and so therefore it might have been written as 1 over 10 squared or 1 over 100. Okay. So following this idea, now let's take a look at a mixed number. So let's say you're trying to show a student what a mixed number really is. Let's look at this. Let's take expanded, somewhat of expanded form and write as a mixed number. Remember, a mixed number has a whole number component and then a fractional component. So let's say I give you 235. There's our mixed, our whole number part. But then I write it as 8/10, 10 to the first, and 7 over 10 to the second. Well, we know in order to combine like terms, we already have our whole number part. That's done. So this part's finished. But in order to add these two fractions, we have to have like terms. We have to have like denominators. And so we need to ask ourselves, all right, if I need a like denominator, and the good news is these are all powers of 10, I have 10 to the first and I have 10 to the second. So a common denominator has to have 10 to the second go into it. So I have my 235. I have my 8/10. I have my 7 over 10 squared. This goes back to the idea that we can always multiply by the number 1, and we can make the number 1 look like anything we'd like. Since I need 10 to the second power, and this one only has 10 to the first power, I'm going to choose to multiply by 10 to the first over 10 to the first. All that is multiplying by the number 1. And so now I have 235 plus 80 over 10 to the second plus 7 over 10 to the second. So that gives me 235 plus 87 over 100, since that's what 10 to the second is. And therefore we are left with 235 and 87 hundredths. So powers matter. Now I'll leave this up and we'll look at another example. So I'm going to get rid of that part of expanded form so I can use this side of the board. Now, let's say I give you a mixed number and I want you to go backwards. Actually, I want to give you a decimal and I want to make it go back to a mixed number. So let's convert to a mixed number. 28 and 4,756 ten thousandths. 28 and 4,756 ten thousandths. 28 and 4,756 ten thousandths. It's 4 decimal places out to the right, 1, 2, 3, 4. That's in our ten thousandths column. Well, at this point, we just need to reduce. Now, the nice thing is we've already gone over our rules of divisibility. So yes, they both end in an even number. 2 will go into it. 3 will not divide into the denominator because it only adds up to 1 for these digits. So 4 will go into this. 4 goes into 56 and 4 goes into 0. So if we reduce by 4, we're going to get 28 and 2,378 over. Oops, I think I only reduced by 2. I did. 5. 56 would have worked. I mean, 4 would have worked. So I guess we only reduced by 2 here. Now, if I reduce again by 2, I get 28 and 1,189 over 2,500. It won't reduce anymore. And so now we are finished with our converting to a mixed number. Okay, so how do you show decimals to students? All right, I'm going to leave the place value there for just a minute. How do you show to students? We as adults know the end result of working with decimals, but students are going to see them for the first time somewhere around 4th grade, 5th grade. So let's work with a concrete method and use blocks, flats, longs, and units. Okay, so model using a concrete method. Okay, so I'm going to look at blocks, flats, longs or rods, and units. And we're going to redefine what each of these represents. So for example, let's say I give you the decimal 6.2, or properly read 6 and 2/10. Okay, since our place value, since our farthest place value to the right is in the tenths column, it's 1 to the right, I'm going to start with that. And I'm going to say, okay, I'm going to let my smallest unit of measure equal 1/10. And then I'm going to work from there. So that means a long is going to represent whatever the next column is. Okay. So in this case, we now know this represents our 1/10. So therefore, and that's a unit. So therefore, a long represents the ones column. Base 10. So here's our unit, our little tiny cube, and this will be represented in terms of longs. So therefore, I would model by taking out 2 singular units and 6 longs. Now remember, this is base 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I have 6 of these, and I'm not going to do that with all 6, 2, 3, 4, 5, 6. Now a student can see that this is what it would look like using, in this case, longs and units. All right, so let's move to something a little bit larger. And let's say larger, not conceptually, but in number of digits. For example, let's go 3.245. So the key is to figure out what place value the smallest number, the smallest column is. So since we are 3 to the right, that would be tenths, hundredths, thousandths. So in this case, this is going to be your unit. We have to declare what they're going to represent. So a unit in this case, let's see, 1, 2, 3 to the right, that's the thousandths. Which means a long or a rod would be hundredths. Which means a flat would represent 1/10, and I'm just counting thousandths, hundredths, tenth, and the next one would be the ones column. And a block would represent the whole number ones. So if we were to model this and draw it out, we can represent this in a lot of ways. This would say, okay, here's your units, here's your long, here's your flat, here's your block. So we have 3 blocks. I'm going to need this space, so I'm going to get rid of this. I would have 3 blocks. 1, 2, 3. 2 flats plus 4 longs plus 5 single units. So if we wanted to, we could say, all right, now let's think about what we have. We have 3 ones. We have 2 flats, which are 2 1/10ths. We have 4 longs, each one representing 1 100th. And we have 5 units, each one representing 1 1,000th. So if we needed to write this as an improper fraction, we would need to find a common denominator. Okay. So again, this is, let's see. This denominator is 1 over 10 to the third. This is 1 over 10 squared. And this is 1 over 10 to the first. And this is 1 over 10 to the 0. So our common denominator has to be 10 to the third. So we need to make each one of these terms separated by plus or minus, having a common denominator of 10 thirds, 10 to the third. So I have 3 times 1 over 10 to the 0. Since I need that to be 10 to the third, I'm going to multiply by the number 1, and I'm going to make the number 1 look like 10 to the third over 10 to the third. Then my next term is 1 over 10 to the first. Again, I need a common denominator of 10 to the third, so I need 2 more 10s. So I'm going to multiply by the number 1, looking like 10 squared over 10 squared. Next term, I have 1 over 10 squared, but again, I need it to be 10 to the third. So I need 1 more. So I'm going to multiply 10 to the first over itself. And then the last one already has the denominator we need. And so we already have 10 to the third. So if you needed to write it as an improper fraction, this now gives me 3 times 10 to the third over 10 to the third, 2 times 10 squared over 10 to the third. Remember, when you multiply, The bases are the same, we add exponents. This would be 4 times 10 over 10 to the third, and 5 times 1 over 10 to the third. Simplifying each term, 10 to the third is 1,000. 3,000 over 1,000. 2 times 10 squared, 2 times 100. 4 times 10. 5 times 1. Now that they all have a common denominator, we could rewrite this mixed number as, and here it is up here, 3,245. And what place was that 5 in? Well, we said it at the very beginning. 1, 2, 3 to the right. 1, 2, 3 to the right is the thousands place. So this is 3,245. And since the 5 is in the thousands place, we just showed that our common denominator is 1,000. And there we have it. Writing it as an improper fraction. So using blocks, flats, longs, and rods is very helpful, and we'll look at it again when we look at addition and subtraction. But let's make sure we know the proper way to write these out. So we do this a lot in 2nd grade with whole numbers and place value. 3rd grade, we practice again. And 4th grade, 5th grade, now that we're looking at decimals, we're just redefining and adding to this whole number by adding to it fractions or decimals. So you might see something like the following. Use words, okay? Use words to expand. And I'm going to give you this, 12.345. Well, lining up our place value, since we have numbers on the left side, here's our whole number part. And here's our decimal or fraction part. And then you'll notice we have the decimal in the middle. Wherever you see that decimal, that's our word and. So let's start. We would start with just where we left off. This is the same as our whole number, 12, and, well, we have 3 numbers. We have the digits 3, 4, 5, and we need to ask ourselves, what place value is that 5 in? Well, it's 3 to the right, so that would be 10 to the -1, -2, -3. That's in the thousandths column. So here it is in written form, but it says use words. Okay, so we're going to start off with the whole number part, which is 12. And as soon as we get to the decimal, that's our word and. As soon as we get to the mixed number part, we separate the whole number and the fraction with the word and. So I have 12 wholes and 345. And we have to say 345 what? Well, thousandths. As soon as we put that THS, we know that that's a fraction. Okay. So you may be asked to go kind of back and forth. Keyword, that word and is where that decimal point goes. So how would you show a student, now we're going to look at a comparison. How show a student that 4 out of 17 is less than 8 out of 17. Now, of course, we could do that with pizzas, we can do it with blocks, we can divide something into 17 parts, and we can take 4 of them and show that 4 is less than 8. So since these denominators are the same, we can pretty much compare numerators. We could also take a look at a number line. We could say, okay, on a number line, between 0 and the whole number 1, we have divided this into 17 parts. And that's going to make the entire whole number. Instead of me writing out 17 parts, we'll kind of estimate. Half of 17 is 8.5. So I'm going to call this right here 8. I'll call this 9, 7, 6, 5, 4, 3, 2, 1. So 1, 2, 3, 4 of these 17 is right here. 8 of these 17 is right here. So, and if, of course, I could keep going, 10, 11, 12, 13, 14, 15, 16, 17. So 4 out of 17 is on the left side of 8 out of 17. So therefore, 4 17ths is smaller than 8 17ths. So very similar to what we do with whole numbers. They're both positive, so they're on the right side of 0. Well, now let's compare negative 3/5 and negative 4/5. Negative 3/5 and negative 4/5. Let's say we're not sure which one's greater or which one's less. So let's take a look on a number line. Well, this time they're on the negative side. So here's 0. Here's negative 1. They're divided into 5 equal parts. 1, 2, 3, 4, 5. So I have negative 1 out of 5, negative 2 out of 5 pieces. And again, we could show that if I give you negative 3/5, I'm sitting right here, and negative 4 out of 5 pieces is to the left of it. So if I read left to right, negative 4/5 is on the left side of negative 3/5 is less than negative 3/5. Given the original problem, however, you'll notice I started with negative 3/5. So that must mean negative 3/5 is greater than 4/5. Okay. Now let's figure out, let's compare uh 0.72. Notice I'm not saying it out loud, the proper way to read it, and 0.614. So when in doubt, write them out. 0.72 goes 2 places to the right, so 1, 2 is the hundredths column. So that's the same as 72 over 100. 0.614, 3 places to the right, that's the thousandths column. So that's the same as 614 thousandths. Well, I can't compare unless we compare like terms. So in order to make them alike, they have to have the same denominator. Well, if I multiply 100 times 10, I get 1,000. So all I'm going to do is multiply by the number 1. And I'm going to make the number 1 look like 10 over 10. And when I do, I end up with 720 out of 1,000. And I'm comparing that to 614 out of 1,000. And now we can compare, because they have like terms, like denominators, and we can see that the denominators are the same, but 720 is greater than 614. Okay. And then let's say we don't have, let's say they're both looking identical, and they both have the same number of digits in the same number of place value columns. So let me give you an example of what I mean. So we have two numbers that look almost identical. And yes, of course, we can split them up and we can compare place values to determine which is greater or which is less. We've got the word place. Compare place values. So let's say I give you 12 and then I just go 6, 8, 2, 4. So 6,824 10,000ths. And then I also have 12 and 6,872 10,000ths. So they both have the same place value. They both go out to the 10,000ths column. So we can start comparing. Well, they both start with 12 whole parts. Then if we go to the next digit, so these are the same. Then I go to 6/10 and 6/10. Those are the same. 8 100ths, 8 100ths. Those are the same. And then they change. They change right here with the 2 and the 7. I don't have to go any farther. I now know that 2 is less than 7. And so therefore, my entire number is going to be less than 12 and 6,872 10,000ths. So we can just compare place values. Okay. So it's pretty interesting. Now we've talked about terminating decimals. And if I give you a fraction, I can figure out if it terminates or not very quickly. We have a theorem that will help us. So this theorem, remember, a theorem is a proven fact. This was done many, many years before. So we can use it because it's been proven. So given a rational number, remember, rational numbers are anything that can be written as a fraction. So we're going to call it A over B. So a rational number in reduced or simplest form can be written as a terminating decimal if and only if. So this works both ways. The prime factorization of the denominator contains only powers of 2 and 5. The prime factorization of the denominator contains only powers of 2 and 5. I'm going to put that in a box. So let's take a look at an example. Okay. For example, if I gave you 3 over 25, without having to divide it, now we can, right? We know this. We know that that means 3 divided by 25. Yes, we could add a 0. 25 goes into 30 once. Yes, we could put a place value of 0, bring it down. 25 goes into 50 twice. And we're done. So yes, we can see that this would be the same as 0.12, but you may not always want to do the long division. So instead, we can incorporate this theorem. Okay, and I'll show you how. We're given 3 over 25. According to the theorem, we want to look at the prime factorization. Okay, 3 over 5 squared. Well, we know 5 squared is 25. We know that since we want decimals to be in base 10, I need to figure out, let's see, I want each one of these 5 to be marked with paired up with a power of 2, because 5 times 2 is 10. So I'm going to multiply it by 2 squared. I actually have only multiplied by the number 1. I'm just making it look different. So this is now the same as 3 times 4. This is now the same as, well, it's multiplication. So I'm going to commute and I'm going to associate. And I'm going to rewrite this as 5 times 2. And they're both being squared. So I'm going to condense that to 5 times 2 quantity squared. This now gives me 12. This now gives me 10 squared. That's 12 over 100. So that means our last digit, the 2, has to land in the hundredths column. Tenths, hundredths. So what I want to do is I want to create powers of 10 in the denominator. Let's do it again. Let's say I give you 1 over 8. Well, some of you may know that that's 0.125 if we use long division. I don't want to use long division if I can avoid it. But I do know that 8 is the same as 2 to the 3rd power. Now remember, this is all base 10. So how many factors, how many 5s do I need to pair up with each of these 2s? So I'm going to take and go, well, I have 3 2s, so I also need 3 5s. And again, I've only multiplied by 1. So now that gives me 5 to the 3rd. Using the commutative property and the associative property, I'm going to rewrite that to 2 times 5, both of them raised to the power of 3. Now this gives me 5 cubed is 125. This now is 2 to the 3rd. That's 125 out of 1,000, which means the 5 has to land in the thousandths column. Tenths, hundredths, thousandths. So this will always work if the prime factorization of the denominator contains only powers of 2 and 5. Let's say I give you 11 out of 250. So you can kind of watch. I'm gonna kind of prime factor the denominator. This is the same as 25 times 10. So that's the same as 5 times 5 times 5 times 2. That's 5 to the 3rd times 2 to the 1st. And remember, I want a bunch of 10s in the denominator. I already have 1, 2. I need 2 more. So in this case, now I have 11 times 4 out of 5 times 2 cubed. This is 44 out of 10 cubed. So I now know it's terminating. So this is the same as the 4 has to be in the thousandths column. No tenths, 4 hundredths, 4 thousandths. Okay. Now, same idea. Let's say I give you, is the fraction terminating? Well, let's say I give you 14 out of 35. You might go, ooh, 35 is 5 times 7. Oh, you're right. Well, that's not only powers of 2 and 5. But look at the first part of the theorem. A rational number fraction in simplest form. Well, notice this is 2 times 7. So it wasn't in simplest form. If I first reduce it and make it in simplest form, now ask yourself, is the denominator only factors of powers of 2 and 5? The answer is yes. Therefore, it's terminating. How could I prove it? Turn this into a denominator of 10 by multiplying by 2. And now I have 4/10. And we're done. Last problem we'll take a look at here is, let's go with 4 out of 75. Well, if I factor the denominator, that's 3 times 25. If I factor the denominator to the prime factors, that's 3 times 5 squared. I check to see if it's reduced. I cannot reduce the 4 and the 3, so this is in simplest form. It's in simplest form, but is the denominator only powers of 2 and 5? The answer is no. And so this is non-terminating. It's going to continue forever and ever and ever infinitely. Okay. And so therefore it doesn't terminate. So that finishes up 7.1. I will do a separate video for 7.2. Have a good day.